All right, guys, welcome to class. So, as we get going this first part of the semester, we're going to be doing things a little bit differently. Hopefully, everything works out good. And like I said in my emails, if you guys do have questions, please feel free and ask them. Send me a text message, call me, send me an email, whatever we need to do to make sure that you guys get this information. So, my plan for these guys is I have all the notes that we're going to cover today in our topic 2. I know some of these, the first little bit are going to be a little bit of a repeat for some of you guys because we did cover those the Thursday before we left, before school, before spring break, the extended spring break. So anyway, like I said, I'm going to go through these and then I'll post these videos online to YouTube as well, and I'll post the links onto Moodle, and we will go from there. I will have the normal office hours set up. If you guys do need help, please feel free and reach out. Like I said, we'll get a Zoom classroom meeting set up on the days that we would have theory. So all the days between 1 and 3, they will be available. I will be there waiting for people to sign in. I will send out the new links if it has to change, or if I'm going to try and keep it the same. So all I have to do is click onto it, log in, and you'll be there. Like I said, I'll have those going all day. From 1 to 3 for sure, and then if we need additional help, we can always create new meetings and go from there. But like I said, we're going to go ahead and just get started with these. So all I'm going to do is I'm just going to go through these notes. Feel free to pause the videos as you guys need. Rewind them if you need to go back over the information. That's going to be the easiest thing to do. And like I said, if you do need some more assistance, please reach out, and I will, I'll cover things again or do what we need to do, but I'll make it up to you guys. Or make the information available to you guys however we need to work it. So with that, let's go ahead and continue on. So in the previous weeks, we had talked about how capacitance works and resistors work in AC circuits. Now these are just the capacitors, just the resistor circuits. So now when we get going, we're going to be doing more difficult circuits. They're going to include both resistive and capacitive components. Next week, we're going to be talking about resistive and inductive components and learning how an inductor works, what its properties do, things like that. And then we're going to continue on. And the week after that, I believe we're going to start getting into filters. And those are really the kind of the fun parts with the RL and RC circuits, that they allow you to control frequencies. You can now sift out the frequencies you want. You can find different ways to interact with them, things of that nature. So those are things to be looking forward to. So again, I apologize if we have any big goofs or issues. Again, this is kind of the first test run, so hopefully everything works the way it should. All right, so as we're talking about RC circuits, some of the things we have to determine is we need to kind of go through our definitions again. So we have a resistance. Now resistance is designated by the capital R. This is our real values, okay? So if we look on our chart to show the relationship, everybody, over here on this horizontal axis, this is our R. This is where the real values live. On the vertical axis, on the top, this is going to be our positive J, or I, however we want to do it. And these are going to be our X of L, so our inductive reactance values. And down on the bottom of the vertical axis, this is going to be our minus J. This is going to be our capacitive reactances. So right now, this week, we're going to be primarily down in this realm as far as finding total impedances, things like that. And again, the impedance is just a combination of the two, between our resistive and our reactive components. Those values we're going to combine together to form some new value. So in this case, we have this line is going to represent the impedance. So again, as we said, so we have resistance is designated by our capital R. That's our real values. Those are the things we can measure day to day. The next one, going along with resistance, if we take the reciprocal of resistance, we're going to get G, which is our conductance. Now, conductance is measured in Siemens. And resistance, remember, that's measured in ohms. This is designated by the omega. This is designated by capital S. Now we have resistance. We also have our reactance. That is designated by a capital B. These are our imaginary values. They only exist when we have an AC signal present upon them. So it's not something that we can measure, but with the AC signal present, they act as resistors. They oppose the flow of electrons, and that's their job. And we can actually see that. And you guys have been seeing how with the capacitors, how they split up the voltage drops. They act just like resistors in that manner. So we have reactance, and if we take 1 over our reactance, oh, I'm sorry, I screwed this up. Reactance, sorry, is designated with X. I apologize. So we have X of L, X of C. So that's just designating inductive reactance or capacitive reactance. I apologize, I got ahead of myself. Reactance is designated by X. So when we take the reciprocal of X, that gives us B, which is our susceptance. That's basically how susceptible is an AC circuit to ignore the change. How easy is it to get a signal to go through it? And that's kind of where the reactance comes into play, where we have resistance, reactance. They're both opposing the current. They do the same thing. We just have named just a little bit differently so we can keep track of the different parts that we're using. And I'll be trying to use these terms more and more as we go on to designate their different functions and where they come from, how did we get these values, things of that nature. So we have our reactance, it's our imaginary values. This comes from our capacitors and our inductors, which I know we haven't talked a whole lot about those, but we will here next week when we get into those guys as well. So we have a resistance reactance, and now we need the combination of the two. So we have our impedance. Now impedance is designated by a capital Z. And like I said, this is the combination of our real values R and our reactance values X. When we combine these together, we can't just add resistance reactance together because they are out of phase and they won't directly add. So the reactance is the sum, using Pythagorean's theorem, is the square of the sums, the square root of the square root of the sum of the squares of the resistance and reactance value. So it's the combination of the two. And like I said, we'll talk about this a little bit more, and hopefully it'll make a little bit more sense here shortly as to far as what we're doing with those. So when we take the inverse of impedance, we designate this as Y. This is admittance. Now admittance, like we said, just with conductance, susceptance, those are the opposite of it. It's measured in Siemens, and it's just a collective term for how much does the circuit actually go through. With conductance, how well does a material conduct? If it has a high conductance, it's going to have a low resistance. If it has a high resistance, it's going to have a low conductance. Same thing with any of these guys, with the reactance versus the susceptance and the impedance versus the admittance. So again, over here we have our graph of all these guys. So we have our resistance, our capacitive reactance, and our inductive reactance. And then in the middle, we have the impedance, which is the total. So when we have our impedance, because remember, impedance is the total opposition to AC current. So I'm going to write this back out again. Impedance is the combination of both resistance and reactance to give us the total opposition to AC, to changes in AC. And when we have impedance, we can display it in one of two ways. So we can display this information in rectangular form, and we could display it in polar. Both of these have their uses, and both of them have, pros and cons for them, but they represent the exact same information. So now let's take a look at rectangular form first. So rectangular form is when we display the information in the following format, and we can display. It's really easy to find out which parts are which. So our total impedance is equal to the real components plus or minus J of the reactance totals. So in this case, we just use J as a designator to signify, hey, this is a different value. These are not going to add directly, so we're looking at something completely different than just the resistance. So in here we have Z is equal to the impedance, R is the resistance, and X is the reactance. Now, one thing to note is that when we're looking at here between the X values to find out if it's a plus or minus J, it's a plus J due to the capacitor. It's due to it's plus or minus J due to if it's a cap or an inductor. Okay, it's plus J if it's an inductor. It's minus J if it's a capacitor. Okay, so that's the format that we're going to use for rectangular. We use rectangular form to add and subtract. So when we add and subtract our values, we want to make sure things are in rectangular form so that the same things get added together. The real values get added to real, imaginary get added to imaginary. And then when we get done with that, we'll come up with just a final answer where we can combine everything together into just one simple real term and one simple imaginary term. And then from there we can go on and do different math functions. So polar form, going to do this to separate a little bit. So we have our polar form. This is the combined value of the real and the reactance values with its associated vector. Basically implying we are going in a direction at a certain angle. Okay, so with that, the standard form for polar form is impedance is equal to the magnitude of it at some angle, where Z is the actual impedance value and this is the phase angle. Now, as we talked about before, when we have just capacitors, the phase angle is 90, and so that's going to shift things a little bit. But in reference to each other, there will not be a phase shift. The cool thing is then once we get into RC circuits, we can actually calculate a lot based on what that phase angle is. So we may not know what the capacitance of the circuit is. We may not know what the resistance of the circuit is, but we can calculate it based on the phase angles that the two waveforms have together. And so that's what we're going to be looking at primarily coming up is that what's the difference in my phase angles? How are these going to look on a graph? And so once we get these going too, we're gonna go through the calculations. We're gonna come out with what the final values are, what the phase angles are, and then we're gonna graph these out. That way you guys can see them when we get back into lab, or we get the lab equipment to you guys on the scopes, that you can actually see this phase shift between these two signals. And it actually will start to make sense of, okay, well, this is why I'm doing this. This is why they don't add, because they literally don't stack up to each other, and you can't use them to add. They're not in phase. They won't add directly together. Okay, so also remember as we get going that when we are talking about these guys, so when we're trying to solve for these, we're going to be doing a lot of right triangle math. This is why we covered it at the end of DC last quadmester. So as we go through these, remember that that's where these formulas and these conversions come from, is using right triangle math and their relationship with one another. So as we get going, let's remember a few things, okay? We have this, these acronyms that we can use to kind of remember the order of how things are supposed to go. So remember, SOHCAHTOA. So the SO is the sine of an angle is equal to its opposite over hypotenuse, okay? the cosine, or the ca part is equal to the cosine of theta, or our angle, is equal to the adjacent side over our hypotenuse. And tangent, which is the TOA, is tangent of theta is equal to the opposite over the adjacent. Now, how does that look as far as reference to our triangles? Well, remember, when we're building a triangle, we have our real value, we have our x of L, we have our x of C. When we come through, we're going to be building this triangle. So theta is right here. This is the total impedance. This is going to be the capacitive reactance, and this spot up here is going to be the resistance. So if we look at the sine of theta, which is opposite over the hypotenuse. So the opposites over here is the x of C, and over here the hypotenuse is z. So then we can just plug these values in depending on what we have to solve for what we need. And then also we have Pythagorean's theorem. So when we're trying to solve for z, remember that z squared is equal to r squared plus x of c squared, because we're dealing with x of c. And remember that translates from a squared plus b squared is equal to c squared. This would be a, this would be b, this would be c. So that's how we translate it over. And when we're done, we want to be able to solve for just the total impedance. We want to get the z by itself. So we end up with the square root of r squared plus our reactance value squared. So that's where we come from. So the other way that we can do it is we're also going to be converting these back and forth. So again, we're going to look at what do we have, what are we given, where are we trying to get to. So in these problems, most of the time we're going to be given a resistance value, we're going to be given a reactance value. We have to use those two to solve for what this impedance is. Well, since we're solving for that, we're not going to use the value we get in these calculations. We just want to use the values we're given. So in this case, to find our theta, we come back over and look at our options that we have. Well, if we look, we have the sine. We can use the opposite, which we have, it's our capacitive reactance value, or we can look at our hypotenuse value, which is z. We can calculate for it, but we're not given it. So, and we don't necessarily want to use that formula. So that one's out. So we look at our cosine. Again, we have the adjacent, which is the real value, but again, we're left with the hypotenuse, which is this value that we have to calculate. So we're like, okay, let's see what else we have. What works better? So we come back to our tangent. So we look at our tangent of our theta, and we have our opposite over adjacent. Perfect. We have the opposite, we have the adjacent. So when we're in this, we can find our total resistance value and the total reactance value, run it through these calculations, and we can easily convert it into its polar, total polar value. So in this case, we have our theta is equal to the arctangent. So we take the arctangent of both sides. That's going to cancel tangent and tangent. Arctangent is going to be equal or multiplied by the opposite over the adjacent. And that is how we get those two values. Okay. This is also known as going from rectangular notation into polar notation. So we're able to go from these points. Now remember that this point here, right here at that point where we're marking in, we have our r and our x of c value if we're looking at a graph. Okay. This is polar. We also have our z is equal to r minus j x of c value. And this is what we're doing. We're taking this information and converting it into our polar notation. Okay, so one thing we want to look at is let's look at an example of how we're doing this. Okay, so we'll come back here. We're going to draw out our figure. So we have R is equal to 16 ohms. While we have our circuit, we come up with our x of c value is equal to 6.079 ohms of reactance. Okay, now we want to find what is the z and what is our theta. Because most of the time when we're looking at stuff, we want things in polar notation. It's easier to see on scopes, graphs. I mean, this is what we're going to use to multiply, divide, things like that. So that's the other big key is polar we use a lot because then we can do our multiplications from it. Okay. So in this aspect, we have R is equal to 16 ohms, X of C is equal to 6.079 ohms. So our Z, or as we recall, we come up and look at our original formula, so we're using Pythagorean's theorem, is the square root of R squared, which is 16, plus our reactance squared, which is 6.079 ohms. So we square those two, add them together, take the square root of it, and we end up with a total impedance of 17.115 ohms. Perfect. We have our equation right there set up for what it is. Now what we need to do is we need to find this angle. So our theta angle is going to be equal to the arctangent of the opposite, which is our reactance value. So we're going to put in a negative 17.115. And the reason we put in negative is because when we look back at this formula, and I should expand this out a little bit more again. So this is the arctangent of the opposite, which is plus or minus our x value divided by our real value. So again, referring back to here, if it's a capacitive reactance, this is negative J. If it's inductive reactance, it's a positive J. And since we're down here with the negative J, we want to put the negative value for that. In here, it doesn't matter if we put it in or not, because if we have a negative times a negative, it's going to end up positive anyway. So in this case, in this instance right here, we don't have to worry about checking for that sign because it's going to be taken care of anyway. So we end up with the negative 17.115 over 16, and then it's the arctangent of that ratio. So we end up with theta is now equal to negative 20.804 degrees. Okay, so there's our theta. So then we have our final Z total for this entire circuit. So the entire resistive nature of this circuit is going to end up being 117.115 ohms with an angle of negative 20.804 degrees. And that's it. That's the things that we're looking for. Now we can take this value and we can go through and we can use it to solve for our currents. And then once we have our currents, we can solve for the voltage drops across everything. And as we go, that's what we're going to practice with. We're going to start off with a simple series circuit that has a resistor and a capacitor in it. And we're going to solve for all the values in there. And then we're going to move on. We're going to do a couple of those, and then we're going to move on to some more difficult problems. And then we're going to get into parallel circuits and then series parallel circuits. So for right now, that's where we're going to end, and we will pick it back up when we start solving a basic RC circuit that has one resistor and one capacitor.